Dive right into this presentation I have for you today. It's a weather analysis, and it's an excerpt from a presentation that a colleague and I had given once before, and we gave it at a Mentor Live presentation, which was to the National Association of Flight Instructors. We've also given this presentation at AirVenture. And I gave this in conjunction with Dr. Ian Johnson. He's a human factors expert who also works in the FAA's Aviation Weather Division. And so here's just a brief overview of what I want to cover today. Got to talk about what we do in the FAA Weather Research Branch, toot our own horn a little bit, but then just talk about what we see as a problem when it comes to aviation weather. And then I will get into an analysis of an actual accident itself. So we're just going to keep going along here then. The FAA, our program objectives within the Aviation Weather Division, we are in the Weather Research Branch, and we're divided into two programs. First one is the Weather Technology in the Cockpit program, and the bulk of their work is developing standards for weather information in the cockpit, but also to help resolve meteorological related gaps, especially in the understanding and interpretation of weather information by pilots. And I'll give you a little bit more information as to why they're really focusing on that in the next few slides. Now, the work that I'm directly involved in is with the Aviation Weather Research Program. This is where we either enhance existing products or develop new products for aviation weather. We've got work going on in the forecasting of thunderstorms, my principal area of in-flight icing, but also turbulence, clouds, visibility, and we've recently started some work with space weather and the impacts of that at high altitudes, for example, and disruptions to communications and things of that nature. But let me also put out right now an invitation, really, because we do a lot of evaluations and we're looking for participants in taking part in our evaluations. We do a lot of remote work. So as a pilot, if this is something that you'd like to be involved in, my contact information is at the end of this. Please send me an email or get in touch with me one way or another. Because as I said, we're always looking for pilots to participate. We want feedback to let us know if we're on the right track in different areas. So what is the problem that we're trying to fix? And it's a two-part one. The first part that I want to focus on here is the gaps in weather knowledge from pilots. These are some results from a study that Embry-Riddle Aeronautical University did for us. And if you look on the left-hand side, the overall performance in interpreting IMC weather information, you can see there's student pilots in the graph that came in at 49%, private pilots 58%, and then instrument rated, that is private and commercial, well, they did better. But don't get too excited because it's a 65%, which in a lot of places, that's not a passing grade, and it's really not significantly higher. And so even at the instrument rated level, there are gaps in understanding and interpreting weather information. On the right-hand side are some scores for some specific weather products. And you can see somewhere around the 50% range, for example, weather radar and air mets and the interpretation of those on the left, and then getting up to 77%. Again, some improvement, but overall, not what you would necessarily want, especially since weather is so critical to flight operations. So in addition to the gaps that we know that are there in the understanding by pilots, let's look at some recent accident information. This is from the latest AOPA Air Safety Institute report. Used to be called the Null report, is now the McSpadden report. But if you look over the last 10 years, and what this graph is showing is general aviation accident trends over the last 10 years, what myself and my partners here in the aviation weather branch, what we really find intriguing, fascinating, troubling, all these types of things, is how constant the number of accidents is from year to year to year, relatively. We had a slight drop in 2020. Pandemic did some strange things to everybody, but unfortunately, 21 and 22 climbing back up, right around 1,000 accidents every year. The fatality rate, which is the dark line, the dark area at the bottom of this graph, also fairly constant year to year to year. Now, you might say that, well, who is this happening? It's probably just the private pilots, the student pilots. Well, but that's simply not true. As you look here on the left-hand side, the pilots involved with all non-commercial fixed-wing aircraft accidents, you see as you look down the third row, the private pilot accounts for 46%, almost half of those. But you look on down furthermore at the very bottom, and IFI pilots on board, almost, between those two, and it could be some of the same, but the IFI pilot on board, still half of the accidents occurred. A CFI on board in a quarter of the accidents, commercial rated up at the top, nearly a quarter of the accidents. So it's happening across all the ratings of pilots. It's not just a private or a student pilot issue. And when you look on the right-hand side, when it comes to weather accidents themselves, we see that the statistics are very, very similar. It's not just a private or a student issue, but it does include commercial pilots, IFR pilots, even CFIs themselves. NTSB accident reports for the period 2008-20 through 2022. During that period, the graph on the left with the pie chart shows that the total of all the accidents, weather-related, was 22% of those, and of those, over half of them were due to adverse weather. On the right-hand side is the fatalities, or the weather-related accidents that led to fatalities, where adverse winds caused more than 50%, they were 11% of the fatalities. And what's very interesting is that low ceilings and visibility on the left-hand side, which is that red area in the lower left, accounted for 15% of weather-related accidents, but they almost are always fatal. In fact, 41% of fatal weather-related accidents were due to low ceilings and visibility. And then there's a mixture of all kinds of other ones, which in-flight structural icing is one, thunderstorms, turbulence, all contribute to this. And again, these statistics they tend to remain constant year after year after year. And so we ask ourselves, why is that? So we know there's a lack of understanding the correct interpretation of weather products. We know the accidents are remaining at a constant number despite increases in technology. I mean, the cockpit has improved, look at the lower left, from what was once to what we are now. Great improvements. Weather products have improved. On the lower right-hand side, you see an example of a radar-like forecast product using a very coarse resolution weather model. You get these big blobs. Well, we now have the capability to produce more realistic-looking weather forecasts that actually look more like the weather, but yet, as I've said, the accidents tend to remain. So is there something that we're missing? Well, let's look at a particular case and let's see if we can gain some insight. So this was an actual NTSB accident investigation I'm going to look at. It was with a Piper aircraft. It's the actual weather that was used here. And I just want to put some caveats in here that I'm not here to teach you how to fly. I'm a meteorologist and atmospheric scientist, as Mike said. I'm not a pilot. But I want to give you some information. And these are not requirements either, but it's suggestions, it's recommendations to help increase your weather knowledge and to help you ultimately avoid weather hazards. So actual NTSB accident investigation. I participated in this investigation with the NTSB, and it was quite eye-opening, and we have a very good working relationship with the NTSB on these. And so this is where this information came from. Here's our situation. Here's our aircraft. This accident occurred near Danville, Arkansas, which you'll see in just a little bit coming up. That's in the western part of the state. Happened in April of 2021. That's springtime in the South, where you can get all kinds of different weather. It was an IFR, general aviation flight, planned flight of a flight level of 23,000 from Muskogee, Oklahoma to Williston, Florida. You look at the pilot involved here, multiple ratings for this pilot. And so there was another private pilot on board, and the accident time, as we noted here, 1700 Central Daylight Time, happened in the evening. And having said that, though, I want to also give some information, though, that even though this pilot had multiple ratings, there was also multiple notices of disapprovals when the pilot failed various practical tests for flight certificates or ratings in areas such as navigation, slow flight and stalls, principle of flight, turning tendency, just a few of them. Going back and reviewing the airman knowledge test reports, that found out that there was some incorrect answers over multiple exams, including meteorology, aircraft performance, aeronautical decision-making, angle of attack characteristics. I bring these up not to say this pilot was wrong, or, because all of us fall short, all of us make mistakes, all of us get questions wrong, okay? But when that happens, that should be an opportunity for us to say, this is an area where I need to do a little bit more education. I need to bone up on this. I need some additional training, okay? And again, not pointing fingers, just the statement of the facts. I want to also note that this airplane was equipped and certified for flight into known icing conditions, but there are limitations and there's warnings that come along with that. It doesn't give you a blank check just to go off into any and all conditions. So here's the flight track, and let me give you some information. You look at the left-hand side, this particular aircraft took off around 1622 out of Muskogee on a southeast heading, gradually climbing to its intended flight route of 23,000 feet. According to ATC information, at about 1633, ATC broadcast a center weather advisory for thunderstorms in the vicinity, and they advised the pilot about moderate precipitation along the route of flight. About 1651, and we're getting over onto the right side now, or getting close to it, the pilot advised that they were climbing through 16,000 feet MSL. Let's see, not too long after that, as the airplane climbed through 18,600 feet, its ground speed was 171 knots, and then we saw a gradual reduction in ground speed, which began. And again, starting to look at the right-hand side, which is the flight track for the remaining duration of this flight, after reaching approximately 20,000 feet, the airplane began to descend on a southeast heading. And just before it began to descend, the airplane's ground speed decreased to 145 knots. No further radio communications were received, and the pilot did not respond to repeated calls from air traffic control. About 2 minutes after the descent began, the airplane began a right turn to the northeast and continued on that heading for about 30 seconds. The flight path then became erratic before the data ended. The NTSB examination of the wreckage indicated that the missing wing and tail sections were not found with the main part of the aircraft itself, indicating that there was separation in flight due to overload. The recovered airframe and engine were examined. There was no evidence of pre-existing mechanical malfunctions or anomalies. The cargo was secured and removed from the aircraft, and it was weighed, and it was found that the airplane was about 361 pounds over the maximum gross weight. It's important that, according to the FAA Pilot's Handbook of Aeronautical Knowledge, an overloaded airplane may exhibit unexpected and unusually poor flight characteristics, including reduced maneuverability and an increased stall speed. It's important because when you look at most accidents, it's a chain of events, that if the chain was broken anywhere along the line, the accident most likely would not have happened. An overweight airplane, then flying into adverse weather, you're limiting the performance of the aircraft, and it cannot respond as you may think it would underneath other situations and circumstances. The pilot did receive a pilot weather briefing. In fact, received multiple ones, and that's a good thing. It's something that we really do stress a lot with the FAA. I want to put to bed the idea that the FAA wants you to do self-briefings and doesn't want you to call flight service. That simply is not true. And I'll talk a little bit more about that towards the end. But this pilot did contact Leidos Flight Service multiple times. Also got information from FAA. And the last update on that was 1525. And so had all that information just prior to takeoff. Some of the information that was reviewed indicated that the pilot was aware of the conditions forecasted on the route of flight before initiating the flight. And the vertical cross section that was provided by ForeFlight indicate that they would traverse an area of forecast moderate icy conditions. We ask ourselves, was something else missed? And we simply do not have any way of knowing. But pre-flight weather briefings were conducted. Well, let's look into a little bit now at the big picture. Here's our flight path, as you can see, going from Muskogee, Oklahoma, down to Williston, Florida. I'll pull up a surface map at the time right before, or that was valid at the time that the flight took off. And there's a couple things here that come to attention for me. Is that this flight path was north of a frontal system. As you can see, the frontal system extending from Mississippi, New Orleans, up through Texas-Oklahoma border, a low system back in the panhandle of Texas. These are important because the NTSB has documented that many weather-related accidents occur in the vicinity of low-pressure systems, and they occur in the vicinities of fronts. That's where a lot of the weather occurs itself. So automatically we see, yes, I'm in the vicinity. I need to pay attention to the weather, of course, what might happen. Something else, or a couple other things that you can readily pick up off of this map. And my intention is not to make you a meteorologist, but at least to pick up some general weather knowledge. You see that the overall flow of the wind, it's coming off the Gulf of Mexico, a general southeasterly wind that's flowing up off the Gulf. It's bringing that warm, moist air off the Gulf, over the land, up and over this front, giving some gradual lift. You're getting cloud cover. In fact, if you look through eastern Texas into Arkansas, Louisiana, and even into western Mississippi, you see that virtually every single station is overcast. So right away, by just looking at this, the big picture is I've got a very moisture-rich environment, a lot of cloud cover. I'm in the vicinity of the front, heads up for potential weather. Now, another product that I really like to utilize and tell pilots to look at is the Storm Prediction Center, SPC, Convective Outlook. This is not an aviation weather product, but I think it's very useful because it gives you an overall sense of where thunderstorms and severe thunderstorms are expected to happen. The light green area is thunderstorms. The darker green area is the likelihood, marginal likelihood of severe thunderstorms. Severity to the Weather Service is tornadoes, large hail, and very strong winds. For aviation purposes, any thunderstorm needs to be avoided. So whether it's severe or not, heads up, be on the lookout for them. The yellow area in here is for slight likelihood, and the darker kind of mustardy area is an enhanced area. These are basically saying that from marginal to slight to enhanced, we're going from limited organization and coverage to increasing organization and higher concentration of storms with various levels of intensity. So right away, without looking at anything else in detail, but just the big picture, we know we're in a moisture-rich environment. We know we're in an environment that has the potential for thunderstorms. Let's dive in and look at some more information. And what is it that we can look at? Well, if we go to aviationweather.gov, which is maintained by the Aviation Weather Center, we can look at the graphical forecast for aviation. Here's the forecast that was valid at 1600 local, 2100 UTC, just a little bit before takeoff. And what we see in the colored areas is a wide area of reduced surface visibility, IFR conditions. But what we also see is that there are numerous thunderstorms and showers over much of the region. And if you even look into like western Arkansas and those things, the symbols that we have there are for severe thunderstorms. But they cover this entire area. The next update 3 hours later for the same forecast time, conditions really have not changed a bit. So a very high likelihood for thunderstorms and showers along the route of flight. What about cloud information? This is also available via the GFA. And what we see here is that the colored area, basically the darkest color is overcast conditions, and we have broken to overcast over a large area of the flight route itself. The next forecast that came out 3 hours later update are valid for the same time. Again, conditions have not changed that much. Again, we have a very moisture-rich environment, deep clouds. If you look at the information on these, the grids through there, in addition to the color coding, it gives you the cloud bases and it gives you the cloud tops. It gives you information about the layers, so you can know what where the ceilings are, how high they go. We're anywhere from bases at 1700 tops all the way up to 36,000. So deep clouds, thunderstorms, and showers on our route of flight. Ground-based weather radar, very valuable tool for you to use. What I'm going to show here is what the weather radar was showing up to taking off. And if we start at 20Z, which was 1500 local, is what we have now. You can see that there is precipitation areas primarily to the southwest of the route of flight. But as we step forward in 15-minute increments, we see that this area is moving towards the northeast pretty steadily. The 2100 here, we see there's some information. We see some of the precipitation is has already moved into the anticipated route of flight. Let me give you some warnings though about ground-based weather radar. It should not be used for tactical maneuvering, even if it's coming up into your cockpit, due to latency issues. What this shows you is where the weather was. It's on the order of several minutes latency, so it's not necessarily real time. It's near real time, but do not use this for tactical maneuvering. But in our case, it continues to show a steady progression towards the northeast into our flight route. So by the time of 2200, you could see how it has moved steadily there. Icing. was a concern. It was briefed, and it turns out that based off our investigation, it turned out to be a contributing, if not the primary factor in this accident itself. Here's the icing forecast information that was available. What I'm showing across the top is icing probability from the forecast icing product, again, available at aviationweather.gov. From left to right, at 3 different flight levels of 14,000, 16,000 in the center, and 18,000 on the right-hand side. What you see is that there is areas of the high probability of icing, 50 to 60%, that this aircraft was going to be going through. Now, what the icing probability tells you is just simply that there is the likelihood of icing. It doesn't give you any indication of the type of icing or the intensity of the icing. But the bottom row does give intensity or severity. And so also from left to right here, flight level 14,000, 16,000, 18,000 shows that in addition to the high probabilities, there's also going to be, this airplane is going to be flying through moderate to heavy icing conditions along its planned route of flight. Moderate icing is defined by the forecast icing product as a 1/4 inch of ice is expected to accumulate in 5 to 15 minutes. Heavy icing is a 1/4 inch is expected to accumulate in less than 5 minutes. It doesn't give you necessarily a lot of time to react. The pilot's operating handbook tells us that severe icing may result from environmental conditions outside of those for which the airplane is certified. This particular airplane was certified for flight into icing conditions, but not all icing environments are the same. Freezing rain, freezing drizzle, what we normally call these supercooled large drops, may result in ice buildup on protected surfaces beyond the leading edge of the wing where pneumatic boots may be. These large drops will hit, and they do not freeze immediately on impact, but they can run back on the top of the wing and on the underside of the wing, and then freeze on those areas where the ice protection systems will not be able to shed them. Bullet number 2 here, again, from the pilot's operating handbook itself, is just because there's de-icing equipment does not imply the capability to fly into forecast or known icing. The equipment is there to provide options in order to take appropriate action to avoid icing. Bullet number 3, icing conditions of any kind should be avoided whenever possible. Does that mean that you never ever fly if there's a forecast of icing? No, not necessarily. What is your aircraft equipped for? What are you proficient at also? And what are your personal minimums? But still, the best course of action is to avoid. And then the last bullet, the airplane is not designed to operate for an indefinite period of time. The de-icing equipment there is there to help you get out of the situation, so use it appropriately. Well, as I said, I participated with the NTSB with this investigation, and I was able to use some of our resources that we have available to us, and that some of our researchers that we fund at the National Center for Atmospheric Research, and they reran this case, doing some information for us and looking into some things in more detail. So this is one thing that they did, is they looked at the radar analysis in more detail. And I'm going to let this run through a few times, but on the top right is the maximum reflectivity. Looking down, the black line is the flight path, the red dot is the position of the aircraft as we go through in time. The bottom right is a vertical cross section along the route of flight that's looking at the reflectivity in this vertical cross section. And as we go through here, I want you to focus on something. We take off, here we go, we're below precipitation, and then right here, where I stopped this, If you look where the airplane position is in the bottom graph, it's just about ready to enter an enhanced area of precipitation that's around 120 kilometers along the route of flight away from Muscogee. This enhanced area is basically an updraft that is happening within this area of convective weather, of thunderstorms. Now, it's not very strong. It's about 25 dBz at most, but it is an enhanced area and it is associated with an updraft. And this, in our analysis, became very, very important. And we really do feel that this was a substantial clue into what happened. So again, let me just let that keep running one more time. And so you can see, and after going through this area and continuing on, that is when issues started. And notice that that area was well below or well above the freezing level, well below 0 degrees. So you're in these sub-freezing temperature realm. So our research team at NCAR also went back and looked at some model information. And by model, I mean a weather prediction model. And we looked a little bit more in depth at what it was showing in regards to liquid water and ice, also ice crystals, snow. And if we go from left to right here in these graphics, this is liquid water content, how much liquid water was in this region at the time. The second one from the left is ice water content. And you can see just right here that most of the conditions at this time were what we call glaciated, i.e. most of it was ice crystals, but there was some liquid water content available. The third from the left there is the mixed phase, the total water content. And so you have some mixture of ice and liquid water content at this time. Liquid water content, again, has to be available. You have to have liquid water at sub-freezing temperatures in order to have the in-flight icy threat. And then on the right-hand side, we looked at where you did have the liquid water. What was the size? What was the maximum diameter of the rain of the liquid drops themselves, what we call Dmax? And what we saw here is that these blue colors, where you did have the liquid water, they were associated with freezing drizzle size drops. Now, it's not an exact match because one of the things with the forecast, there's a lot of uncertainty, but it is picking up overall that the strong convection to the southwest. There was a lot of ice crystals, but there also was some liquid water in here. We then also had our partners at the NASA Langley Research Center. They ran some of their experimental satellite products that these are not available operationally, not available in real time. A lot of the information, though, that for the meteorologist who could be able to take a look at, especially in post-analysis. This one is showing the liquid water path. And if we start at the upper left, we're at 2100 UTC, 1600 local time, and we step through in 10-minute increments. What I want you to focus on is that by 2130, here in western Arkansas, where that circle is, we start to see a red area growing here, which means as we go, if you look at your legend, we go from the greens to the reds, the liquid water path is increasing. Basically, what that's telling us is that there's more liquid water in this area. Then from 2130 to 2140, we see this growing. 2150, it's still there. 2200, it's there also. This coincides with that updraft that we witnessed in the radar analysis. NASA Langley also provided us another experimental product, a satellite icing potential. And if you look at it in that same area of western Arkansas, By 2130, you're starting to see this yellow and red area where the circle is. Yellow is a high probability of light, but the red is moderate or greater is likely, moderate or greater icing. 2140, it continues to grow, 2150, and then at 2200 is when our accident, finally the aircraft impacted on the ground. This was very, very similar to a case that we in the FAA observed. Back in the winter of early 2009, the FAA, in conjunction with our Canadian partners, we conducted a field program called Icicle, the In-Cloud Icing and Large Drop Experiment, where in cooperation with the Canadians, the National Research Council of Canada, we flew their aircraft, well, they flew their aircraft working with us purposely into icing conditions in order to collect data. The aircraft was outfitted with multiple sensors to measure the environment, to measure the moisture in the environment, whether it was liquid or whether it was ice, size particles, updrafts, downdrafts, etc. And what we saw on this particular case, although we saw it at other times too, but on 23 February, we saw that most the conditions were ice particles, ice crystals. However, in our graph, as you see on the bottom right here, these ice crystals, when they grow large enough, they start falling down, precipitating down. They pass through the melting layer, and then as they get down closer to the surface, they melt and turn into liquid drops. What we then saw was that in the areas of updrafts, these liquid drops get caught back up and get recirculated back up into the updraft. And you now are introducing liquid water into what was primarily a ice crystal environment. Now you have the liquid water there. We saw this, we documented it, and so we know it's real, and it was in the vicinity of the updrafts that we saw this. This has led us to modify the current icing product and the forecast icing product SIP and FIP to include this scenario, but we really strongly believe that this plane likely encountered a very similar pocket of supercooled liquid water and or freezing drizzle when it encountered that smaller convective updraft seen in the radar imagery about 120 kilometers from takeoff. Well, what went wrong? The NTSB findings basically revealed that this aircraft likely entered icing conditions that range from light to heavy as it climbed through 14,000 feet about 23 minutes after takeoff, and it remained in those conditions for the remaining 16-minute duration of flight. Freezing drizzle, large drops were likely present. The gradual loss of ground speed was consistent with ice accumulating on the airplane itself. It's likely the capability of the ice protection system was exceeded. We do not know if the boots were activated, how often they were being activated, but they were overcome, and there was a subsequent aerodynamic stall with an in-flight breakup. And as I talked earlier, the aircraft was over its maximum gross weight, which contributed also with reduced maneuverability and increased stall speed. So it's very likely that the structural in-flight icing caused this accident. Well, what can you do in order to be able to avoid these situations? And so, again, as this pilot did, pre-flight weather briefings are very, very important, but do you understand and do you, are you interpreting the products as they should? What can you do is conduct a very thorough pre-flight weather briefing. There's resources available to you. The FAA's put out a very nice advisory circular, 9192. It's not very long. It's not too hard to read, but there's also some very good video training materials out there. There's a YouTube one that's the Pilot's Guide to Pre-Flight Briefing. It's not short, but it has a lot of good information. There's 2 really good videos on the FAST team training site, conducting pre-flight self-briefings for VFR, and then a companion one for IFR. Even if you are a VFR pilot, I would encourage you to look at both of those briefings or both of those tutorials. They're excellent and they can help a lot. Use a structured process when you do a self-briefing. Write things down, document it. And so here's just a sample checklist that came from the VFR module that's on the FAST team training site. Brief early and brief often when it comes to self-briefings. And as I said before, we encourage you to do a self-briefing, but after you've done that, follow up with flight services. Are they seeing the same thing that you're seeing? Are you consistent? Have you interpreted things correctly? And so again, just a great resource. If you've done your homework ahead of time, then you can utilize the Leidos flight services to your advantage. Here are some resources available to you at the top. This presentation will be available to you. You can either do a Google search on these things, or if you have the presentation, there are links to these. The NTSB put out a very nice safety alert. AOPA put out some very good information, and the FAA advisory circular for flight and icing conditions give us a lot of information. I believe as you go from top to bottom on these, they get a little bit longer with each one. So start with that NTSB safety alert for flight and icing conditions. But what can you do to prevent this happening to you? Increase your weather knowledge. If you know you're weak, get some additional training. Understand your strengths or understand the strengths and weaknesses of each product. For example, as I said, ground-based weather radar. It's a great tool, but it tells where the weather was. Forecast information, there's measures of uncertainty with it. And so I would not recommend going right up against the edge of some forecasted weather at all. Give yourself a wide berth, just like you're supposed to give a wide berth around thunderstorms themselves. Be cognizant of how weather can impact your flight and verify the information. Understand the capabilities and limitations of weather displays, as I talked about strengths and weaknesses, but understand your capabilities and limitations. With an aircraft that's certified for flight into icing conditions, and if you're proficient in flying into those, then some icing conditions, trace light, may not be an issue for you. But even if your aircraft is equipped for flight into icing conditions, but you personally don't feel proficient, then the prudent thing to do may be to avoid, to divert, or maybe not even fly. And if we looked in our situation here, a diversion to the north to get around those storms rather than going through them may have made all the difference in the world here. So your capabilities and limitations understand, but also understand those of your aircraft itself. Here's my contact information. I'm the atmospheric scientist, the meteorologist. Dr. Ian Johnson, who participated with me in the larger presentation we give, he is a human factors expert. Please reach out to us if you've got questions, if you want to participate in evaluations, if you want some more follow-up information. We're available for you, and we would love to help in any way, shape, or form. Mike, I'll turn it back over to you if there are some questions, and I'll do my best. So again, thank you for allowing me this opportunity.
Well, Danny, thank you so much. This is incredibly informative and greatly appreciate you sharing your expertise with us. Hopefully this isn't the only opportunity our members will have to benefit from your expertise. First question that came in is, as a member had interacted with you at AirVenture, and he said, as we discussed at Oshkosh, a roadmap to using the various, which can occasionally be divergent, products would be helpful. There are almost too many products, too much information. An explanatory paragraph helping pilots to understand what they each are intended to show and their limitations would be very useful. Any quick comments on that?
I wholeheartedly agree. It's and I have, you know, when I went back to say what was the problem, You know, and part of that is the lack of understanding. Even though the technology has increased, I think part of the fault lies in the weather community. We're very good at putting out weather information, and we're very good at putting out products, but we need to put out that guidance that says, you know, for example, there's, you know, 20 different thunderstorm forecast products available. And so what are the strengths and weaknesses of each one? And they're not all geared for the same users. I used to work at the FAA's Air Traffic Control System Command Center for a while. They were specifically focused on large areas of thunderstorms that covered a certain coverage. The isolated cell was not much of an issue from a national traffic management, but for an individual pilot, an individual cell all of a sudden becomes important. So I wholeheartedly agree. We've got work to do to provide guidance on some recommendations for how to use the products, when to use the products, and what products really should be used for aviation purposes. So yeah, I remember the conversations from AirVenture. Follow up with me some more, and let's get back into this stuff and do some things if we can.
Yeah, that's great. Thank you so much, Danny. Next question up. Is there a recording or transcript of the pilot's conversations with flight service and or air traffic control?
Yes, there are recordings of before the pilot took off. There were some recordings that the NTSB collected. And during, if I remember correctly, there was air traffic control recordings of what was passed along until there was no more radio contact. And some of that was where it was the indication of moderate precip ahead. I think the pilot even asked one time about possible deviating, and the controller mentioned, you know, they're seeing the precip, and it just didn't go anywhere with it. But yeah, there was some information that was available. Excuse me. If you go back, you can actually search NTSB dockets, and in this case, which was I believe CEN 21 FA. I was at the beginning of my presentation of it. You can do a search in the NTSB dockets, and you can get access to all the information that was available and that was documented. Yeah.
Great.
Yeah,
Thank
go
you.
ahead. But let me pause and take a drink while you read me my next question, please, if there are.
Okay. Well, actually, while you're taking the drink, some other questions are coming in, but I promised folks that we were going to do the quiz question at the end. So before we get too involved in the questions and they forget the answers that you gave during the for the quiz questions, let's pop that up, and we'll do that really quickly. They'll be up on the screen for a few moments. Okay, it should be up on everybody's screens. Go through there's 7 questions. The final one is for you to enter in the email address associated with your FAA Wings account if you'd like Wings credit for participating today.
Hey, Mike, and I just noticed that number 2 is missing a B.
Oh gosh. Okay, skip number 2. My mistake.
Yeah, skip it, or else I think I just kind of gave away the right answer also.
Number 2 is B. Both A, well, both now B, both A and B, right?
Yeah, yeah.
Sorry about that.
No, no problem.
Several folks are responding to this. We have 20 people responded to several of the questions, but one person just said they're not seeing the quiz question. So could be on a different screen if you check in the Zoom workplace, maybe on the window, if there's a second window showing, might be there. And we'll leave it open for another minute. About 3 minutes should be enough time to answer the 7 questions. And then we'll go into the rest of the Q&A. Okay, I'll leave it open while we go through these. Danny, first question. Recent research indicates that being instrument rated significantly resulted in improved weather knowledge scores. True or false?
That's a false one. As we said, there was some increase, but not what I would call significant. It was still pretty low. That was 65% still. So that's false.
Thank you. And number 2 is where I was missing the real option B, which is where do most weather-related aircraft accidents occur? A was in the vicinity of fronts. B was supposed to be in the vicinity of low pressure centers. And then we told everybody the answer was A and B. So
right. And again, as the NTSB has documented, low pressure centers in the areas of front. So if you're traversing those areas, if you're near there, heads up.
Question number 3, Aviation Weather Center graphical cloud forecast give information on?
All of the above, bases, tops, and the ceiling heights also.
Perfect. And number 4, Aviation Weather Center icing probability gives the probability of any icing.
That is true. It's not limited to an intensity or a certain type.
Great. Number 5, in-flight icing always occurs over large mass areas.
That one's false, and that's why I was trying to highlight that just in the vicinity of that updraft, you can have pockets of it where it just happens on those ones. Sometimes we think that icing being a wintertime phenomenon is spread out over a large area, and it can be, okay, it can be, but it can also occur in these very small pockets.
Perfect. And last question we'll review is when should self-briefings be conducted? And looks like we did pretty well on that one as well.
Early and often, exactly.
Great. So I'll leave that up in case anybody's looking for their Wings credit email address to enter that in. And we'll go to the next question, which the person's asking, Danny, could you please talk a little bit more about talk a little bit about the speed of frontal boundaries? That warm front looked like it was quite a ways away from the line of flight. So why did that catch your attention? How far ahead of the front could one expect the weather?
Yeah, that's a great question, and that shows some good weather knowledge also. You'll see cold fronts that are moving pretty rapidly. And lots of times the weather will be confined to a narrower band. But in the case here where we have a stationary or we have a warm front, as you go over the front, it doesn't jump up all of a sudden. It's more of a gradual lift. So in this case, it can extend 10 to 100 miles or more very, very easily, if not further. So that's why, first of all, if there's a front anywhere around, first it gets my attention. If it's a cold front, yeah, you're going to have probably a smaller band, but if you're going to have a warm front or a stationary front, and especially if you're on the cooler side of it, that's where you can get these large areas of impact of, a slow, gentle lift of the air. And if it's warm, moist air that's coming off the Gulf, as we saw here, you can get quite an extensive area of clouds. So I hope that answers the question.
Great, thank you. Next question up, is there a measure of the accuracy for the current icing product and forecast icing products?
We do have verification results from evaluations that were done. I don't know the exact numbers off the top of my head here. It's a great question. I can do that. I do know that we tended on the side of being conservative. So we tend to capture, for example, a lot of the pilot reports in our forecast, but we also tend to overwarn a little bit. And that may come back to hurt us a little bit because, there's a tendency that if you go through somewhere that's forecasted to occur and you don't experience it, I think all of us just have the natural tendency to say, those meteorologists, they don't know what they're talking about. Here they go saying it's going to be icing, and I didn't get anything. But we intentionally did that. We don't miss a lot of areas. I won't say we don't, but we tend to err on the side of being conservative. But exact numbers, I don't know, but I think that is a very important piece of information that we need to put in, for example, on the help pages at aviationweather.gov that says, how much are we actually capturing? And I think that could be useful in order to give some confidence in the product itself.
Yeah, that's a great thought. Thank you. And related to this, one of the esteemed instructors in our community says the CIP and FIP were not part of the standard weather briefing at the time of this accident. Training on these products was scheduled to be completed by the end of 2024 and should not be available in a quote unquote standard briefing.
The SIP and the FIP have been around for quite a while. So I'm not, I'd love to follow up with that individual. Yeah, and we can talk some more.
Great, I'll get you guys connected after this call.
Yeah, that would be fantastic because I want to make sure that I'm understanding correctly. Yeah.
Okay, wonderful, thanks. Next question up, what do you consider the best weather forecast presentations for time periods more than 18 hours out?
Oh, wow, great question again, because aviationweather.gov tends to focus on 18 hours, the next one. So, and this is very interesting because the presentation that we did a few years ago to your group, we actually started 6 days out, what you can start looking at. And honestly, it's kind of a hodgepodge of different things. AWC recently added, I think, outlooks out to 3 days or maybe longer of the frontal systems, low pressure centers, things like that, the prog charts. So that's now available looking out there. It's tough, it really is. From an aviation standpoint, I don't have a good answer for you right now, but I can refer back to some of that information that we provided to your group a few years ago, and we listed a bunch of different things, but it meant you had to go to this site and then this site and then to another site. But again, that's an area where I can provide some more information to you on that.
I think that'd be fantastic. Thank you. Next question, is there a table to describe what the different fronts are and what kind of negative issues they result in somewhere?
I would hope there is, but I don't know for offshore. The FAA's weather handbook might have some information that talks about the different fronts and showing the difference between a cold front and a warm front, for example, and how with a cold front you get a very quick lift. It's more like a sharp wedge, whereas the warm front is more of a gradual type of lift. But yeah, I would, the FAA's weather handbook might be a good place to start for that.
That sounds like a good thought. And the last question that came in is, what 1 or 3 weather prediction products would you use?
I wouldn't limit myself to 1 to 3, to be honest with you, because there's so many factors. There's icing, there's turbulence, there's the clouds themselves, there's winds. So you need to get that full picture. I'm probably most familiar with aviationweather.gov, just because I've worked very closely with those folks, and we transition a lot of our products that we enhance or develop over to be run on those sites. I'm not saying it's the best, but it's one that I'm familiar with. But you have to look at more than just one or 3 type of phenomenon. What can get you into trouble is the question I think that needs to be asked. What weather can get you into trouble? And in this case, we saw it's icing. But you remember my statistics. The number 1 for weather-related fatalities is flight into is still in invisibility, VFR into inadvertent IMC conditions. But thunderstorms, turbulence, winds, they all are important.
Absolutely agree. Well, Danny, thank you very much. It's a little bit after 4 o'clock Eastern time, so we're out of time for today's webinar. I think this has been incredibly valuable from our members' perspective. There's obviously a lot that we can explore with respect to aviation weather, and you're clearly an expert that can help us with this. So look forward to future opportunities to engage with you going forward. So thank you all very much for participating in today's webinar. Danny, thank you again, and look forward to seeing everyone again soon. Take care. Bye.